Okay. Let's see. So today we're starting the ANOVA unit. So I'm going to teach you behind the logic of why we use ANOVA instead of multiple t-tests. And then we'll set it up, we'll perform it, we'll interpret it, and then we'll apply it, okay? So let's just review the tests you've learned so far, because you've been on a break. It's been a minute since you ran these tests, right? So if it's qualitative data is for categories, okay? Qualitative, we're looking at a quality. Now, you can count how many people or things possess that quality, but that doesn't mean the numbers themselves have meaning, right? It doesn't make sense to find an average jersey number on a football field, right? So those numbers are actually kind of naming the player so they can keep up with fouls or whatever, all right? So that's an example of qualitative. So if we're looking at a percent, that's also called a proportion, okay? So if you have one sample compared to a claim, that's just a one prop Z test. So if it's a one prop Z test, then your null will be a p-value compared to a claim. I'm just going to put a box. I could make that be equals. I can make that be greater than or equal to. I can make that be less than or equal to. Okay? So the null will be p, which is a proportion, and comparing that to some claim. Okay? So if it's two samples compared to each other, that's a two prop Z test. And the null is going to be one proportion or 1% compared to a second percent. Okay? So those are both if we have proportions. If we're talking about counts, how many things fall into a certain category, then if it's one sample compared to a given distribution, that's your chi-square goodness of fit test, okay? So the main thing I want to remind you for that one is that your observed data goes in list 1, and your expected data or your expected counts go in list 2. So this one, we use the list. Okay? So you're comparing your sample to a given distribution, all right? If you're comparing one sample but looking at two variables to see if there's an association or a relationship, then that's your chi-square test for independence, okay? If you're looking at two samples and comparing one variable to see if the distributions are the same, that's the chi-square test for homogeneity. And remember, for both of these, we use the matrix. Okay? So we put the observed data in matrix A. That's what that symbol is, okay? It's just a square bracket. That means matrix A, okay? And then you run the test. Right? Run the test and then go back into your matrix and check that matrix B, each cell in matrix B has to be greater than or equal to. Do you remember what your expected counts had to be? Do y'all remember?
2.
No, not 2. Greater than or equal to? Say it. What was the second one you guessed? 5. Yep. So you go back into matrix B and you make sure that each of those expected counts is greater than or equal to 5.
Wait, which one of them was a 2?
Which of them was a 2? Oh, N had to be greater than or equal to 2?
It was something like, yeah.
Yeah. Oh. That was the linear regression t-test. You had to have at least 2 points, which we need way more points. I don't even know why that's a condition, but it is. But yeah, that was for the linear regression t-test. Mm-hmm. Thank you. Way to push my brain first thing this morning. I like it. Any questions on if it's a qualitative topic? Anybody? So those are all the tests we've run so far for qualitative, okay? For quantitative, that is if you have measurements. Okay? So if you have measurements and you're looking at means, means is also called averages, okay? So I can say means or averages. If it's one sample compared to a claim, that's just a regular t-test, okay? So your null is going to have mu compared to a claim, okay? If it's two independent samples and we're comparing them to each other, that's a two-sample t-test. So my null is going to compare the first average to the second average. And instead of putting a 1 and a 2, let's say you're comparing average GPAs of males and females. You could put a mu sub M, a mu sub F for male, female, okay? Or maybe you're looking at plant growth. You could put whatever letter represents that plant, like basil, B, compared to tomato, T, or something, okay? Questions? So if it's dependent data, which is what this one is, dependent data or dependent samples, you need to look at the difference in the paired data, and that's just a regular t-test, but only on the differences, okay? So the null for that one looks like mu sub D compared, and usually we compare it to 0. If we're looking for negatives, we make it less than or equal to 0, or we might make the alternate less than 0, so the null would be greater than or equal to 0. If we're looking for positives, maybe we want to see does their grade go up, right? Then we make the alternate be mu sub D greater than 0. So remember, with paired data, that is when you have like a pre-test, post-test, or you're measuring the height of a plant before you give it fertilizer or something, and then you measure those same plants again, okay? So for paired data, it's always going to be the exact same participants or things in your two samples, all right? Any questions on that? So t-test, if it's one, two-sample t-test, if it's independent samples, and then just regular t-test, but only on the differences. So remember, I showed you how to find those in L3, and then we would run the test only on L3. Questions? No? All right. So you'll see there's 2 more blanks right here. So this is what we're going to be talking about in this chapter, okay? So still looking at averages, but if you have more than 2 groups and you want to look at one variable, then that is called a one-way ANOVA. Okay? So you have to have more than 2 groups. That can be 3 groups, 4 groups, 5 groups, whatever. Okay? And you're looking at one variable about those groups and you want to compare the averages. That's called a one-way ANOVA. Okay? If you have more than 2 groups, but you also have more than one variable you're considering, then that's called a two-way ANOVA test. Okay? Any questions? Okay. So lastly, when it was quantitative and I was looking at variance or standard deviation, remember variance is sigma squared, standard deviation is sigma. Those are your parameters, right? The parameters are what we're talking about, what we put in our hypotheses. Then that is a chi-squared test for variance. So that's where you had to use the chi-squared CDF feature to get your p-value. Remember that? And to also get your test statistic, okay? You had to actually find that by hand, remember? It was n minus 1 times s squared divided by sigma squared. Okay. So that's the chi-squared test for variance. And then the last one was if you want to see, is there a relationship between two variables? Now, those two variables, though, are both quantitative. They're both measurements, okay? So when we had two quantitative variables and wanted to see, is there a relationship between them? That was the linear regression t-test, okay? So real quick, let's just review a few parameters. Parameters are about which one, the population or the sample? Population. Remember, keep P with P, okay? So this is what we write in hypotheses, all right? So examples of some parameters, if you're looking at averages, what would that be? What parameter do we use for a population average? Mu, thank you, mu. If we're talking about proportions, P. And if we're talking about population variance, sigma squared. And if we're talking about population standard deviation, sigma, okay? So then statistics are what we find to start talking about our data, yes. Sample data, yes. Good. So keep S with S, remember? So we use our sample to start to get an idea about our data and talk about it before we actually run the test, okay? So if I have mu in my hypotheses, then what should I report out? What sample statistic is also an average? X bar, yes, good. X bar, that's your sample. And if you have normality, in addition to talking about X bar, I'm going to put it in parentheses, you would also report out S, which is your sample standard deviation. Okay. Not only do you talk about the measure of center, which is the average, you would also talk about the variability. So how spread out is your data around that mean, okay? S is your sample standard deviation. If you're talking about P, what is the statistic for P? P hat, good. Sigma squared? S squared, good. That is your sample variance. So you're going to say, my sample variance is this. My hypothesis is claiming that the population variance is this. I think that's really far away from it, so I feel like I'm going to reject the null. That's how we start to talk about data and form an idea. Sometimes we're right, sometimes we're wrong. Sometimes it's not statistically different, right? It's not significant, okay? And it's okay. If you collect data for your SRP or for your final project in here, and you get an idea from your sample statistics, and then you run the test and it's wrong, I don't want you to go back and change it. That's what you thought. That's okay. All right? That's what's cool about a significance test. It allows you to see, if you were to do it again and again and again, are you going to get similar results or different results? Okay? All right, and then last one, which one goes with population standard deviation? What would be the statistic you report out? S. I'm going to give you all a break. You seem tired. Get a stretch in. We're almost done. Come on. You've almost made it through first block. Everybody stretch. Me too. Yes. Okay. All right. Any questions on the previous tests that we've run? Anybody? No? Was that helpful? Okay, great. It's hard to build on if you can't remember all the previous ones, right? But it's been a minute since you did it, so I wanted to talk about that. Okay, so what if we want to compare more than two means, right? We want to compare more than two means. So if you look, okay, I'm going to highlight some so you can see things. So this is a population right here, okay? Everybody see that? That's a population, okay? That's a population. So let's say that population is all college football players. Maybe it's their heights or weights or something, okay? So if I find this value right here in the middle, what is that? That's the population what? Say it again. Mean. Good job. This is mu. This is my population mean, okay? So if I'm looking at all college football player heights, this is going to be that average height, okay? Oh, I wrote mu again. I meant to write mean. Whoopsies. Sorry. Okay, so that's the population mean. So, y'all know my nephew's at Notre Dame. Maybe I'm interested in Notre Dame and I can collect a sample, right? So that's what this first one is. So if I find X bar, let me switch colors actually. X bar would be right here in this sample. This is a sample, okay? This is a sample of Notre Dame football players, okay? What do you notice about X bar compared to mu? What do you notice? Is it far away from it?
Are we talking this way or are we talking?
Well, look, here's X bar, which would be the middle of this sample data, right? And here is the population of all football players. Well, Notre Dame is football players, right? Look at this mean compared to this mean. Is it far away from it? Is it the same? They're about the same, right? So that means I'm going to collect a sample from Notre Dame's football team. I'm going to weigh them all, okay? And I'm going to get that average is the same as if I were to weigh all football players in college, okay? That's what that's saying, all right? Whereas if you look at this next one right here, this sample is still from the population of football players, but maybe this is a sample. Who do y'all watch? I'm just going to make one up. Colorado. Is it CU? Is it like Colorado University?
That's Colorado State.
Colorado State. So CSU, maybe? We're going to make that up if it's not. Okay. If you look at that sample, then the mean is here, right? What do you notice about that mean compared to your population mean? What do you notice about this mean compared to that one? It's higher, which means those football players at Colorado State, because that's what she watches, weigh more on average than my population average, okay? So then lastly, I'm just going to make one up. Let's say this is West Virginia University, okay? I am totally making these up. I'm not making any kind of claims about these football programs.
I know, if it was more accurate, the further off would be like Jacksonville.
Yeah. So let's just pretend though. So I know it's WVU for West Virginia. That's why I'm going with it. Look at that mean. That mean will be right here in the middle, right? But what do you notice about that average compared to the population average? It's lower than that mean, right? It's quite a bit lower. So what this test does is it compares the variability between the means. So if I look at those means compared to one another, if I pulled them all from the same population, which would be all college football players, then you're comparing each X bar, which is your samples, okay, to mu. All right? So that's called the variability between the samples, between the sample means, okay? Now you have what's called, I'm going to use blue, you have the variability within the sample means. Variability measures how spread out the data is. So if you look, this one has a variability that's all inside that population. You see that? In blue right there? I'm back up here with Notre Dame. This is how spread out my football players' weights are for Notre Dame, okay? Whereas this one, CSU, those football players have weights where some of them actually weigh more than my population. Do you see that? So all of those weights, though, are above the mean. All of those weights. All the variability is up here, okay? So half my Notre Dame players weigh more, right? But all the CSU weigh more than that average. That's called the variability within, okay? And if you look at West Virginia down here, their variability is here. They're all below that average, okay? So we don't want to have to do all this every time. That would be exhausting, don't you think? I don't want to have to find all these and try to compare them somehow. You know what I mean? So that is what this does, okay? Your null, and that's what's beautiful about ANOVA, it's always set up this way, okay? You say the average for the first one, which is Notre Dame, equals the average of the second one, which we said was CSU, equals the average of the third one, which we said was West Virginia University. Could I put another one? Could I have had another college and pull an average of weights? Yes. You can have 3, 4, 5, whatever. Okay?
It's good as long as the variable doesn't change, right?
The variable. Right. I'm not going to measure weights at this school and then go over here and measure heights. Right. Exactly. Yep. Good question. So for all ANOVA tests, one-way ANOVA, it's always equals. And then the alternate is always not equals. You don't have to try to do less than, greater than, that kind of thing. Okay? So I'm just going to put mu sub Notre Dame does not equal mu sub CSU does not equal mu sub West Virginia. Okay? So what I'm claiming is that the averages are equal. Those average weights are equal. And then the alternate is that they are not equal. One of them's different. Okay? Or at least one of them's different. We could prove that more than one's different from the others. But at least one of them is different from the others. Okay? All right. If you look, that's just the first one up there. If you look at this one. This sample is inside that population. This sample is inside that population. Look at this sample. Do you think I pulled a good sample if I got something that looked like this compared to these in this population? No. This would make me think this is not from the original population. Right? So if I'm looking at D1 schools, a lot of those D1 schools can recruit heavily, and so they may have heavier linemen, right? And so that's going to pull that average weight up. Whereas some of these smaller schools, maybe this one came from a community college, and so maybe those football players are smaller. So I might think, okay, maybe I need to tailor my population and be more specific and say, okay, I'm going to look at D1 schools and pull samples of D1 schools. Does that make sense? It's also be like, I'm looking at average heights of classes, right? And it's convenient for me to go measure my son's class, right? That's not going to be a good comparison to these classes that I teach. Y'all are high schoolers. He's in 3rd grade, right? So that would be an instance where you're going to get something way down here that doesn't match the rest. Okay, so that's not a good example of running an ANOVA test. You need to make sure all of your samples are pulled from the same population. Okay, same thing with this one. Look how far these are from the population mean. This sample mean is way smaller. This sample mean is way higher. Again, that's going to indicate to me these are not good samples. They did not come from that population of interest. Okay? All right, so why can't I do multiple t-tests? why am I going to run an ANOVA test? Which, by the way, I do want to point out, because maybe I didn't emphasize it. One way ANOVA is called analysis of variance. That confuses some people because they're like, wait a minute, we're not testing the variances. We're testing the means. But you're looking at how those means vary from one another, okay? Or how spread out is that data compared to the other 2 or 3 sets of data, okay? So it's called analysis of variance because we're looking at how they differ from one another, okay? But ANOVA is a test of means. But some people are like, I don't know why they named it that, but do you understand why they named it that? Okay, because you're comparing the means to each other compared to that population mean, and then you're also comparing how spread out are they compared to one another, okay? All right, so why can't I run multiple t-tests? Let's say I want to compare Notre Dame to CSU. I could run a 2-sample t-test for that, right? But I also want to compare Notre Dame to West Virginia. And I also want to compare CSU to West Virginia. That would be 3 separate tests, right? So let's say I'm going to set my confidence level to be 0.95. Then what would alpha be? 0.05. Which means this is the probability of making a type, which one? Yep. Of making a type 1 error, which is when we incorrectly reject the null, okay? So 5% chance we're going to incorrectly reject the null, all right? Then, again, I'm going to use that same confidence level, which means what's the probability I'm going to make a type 1 error for this t-test? 0.05, right? Then same thing for this one. So at the 95% confidence level, what would be the probability that I have made a type 1 error? Well, before I find that, let's find the probability that I don't make an error, which means I'm going to find the probability that I'm correct on the first one and I'm correct on the second one and I'm correct on the third one. Let's find that first, because in my brain that's easier. Okay? So remember, what's the probability that you're correct? That's not a type 1 error. Well, what is that? That's my confidence level. So correct for the first one's going to be what? 0.95. And do you remember in the probability unit, when we say and, what do we have to do? And we do this, or we do this. And is multiply. Good. Or means add. Okay? So if it's and, I'm going to multiply it. Okay, what's the probability the second one's correct? 0.95. Okay? And, so I'm going to multiply. What's the probability that third one's correct? 0.95. So what's the probability that each of them are correct? It's 0.857375. So how do I figure out if I'm wrong? It's called the complement rule, right? Complement rule says the probability of this event subtracted from 1 will give me the probability that it doesn't happen, right? So the probability that I'm correct and correct and correct is 0.857375. So then the probability that I'm wrong or I commit a type 1 error for all 3 is what? It's 1 minus 0.857375, which is 0.142625. Look at that probability. What's the probability that you could commit a type 1 error and a type 1 error and a type 1 error on all 3 of them? Look at that percentage. That's very high, okay? So why don't we run multiple t-tests? because it increases our probability of making type 1 error on all 3 of them, okay? So instead of doing multiple t-tests, instead we're going to run one ANOVA test to compare all of them at the same time, okay? And just think, what would happen if you had 4 groups? You'd be running even more t-tests, wouldn't you? Because you'd have to compare 1 to 4 and 2 to 4 and 3 to 4, okay? So the more groups you have, the higher that probability is that you commit a type 1 error, all right? Okay. The one-way ANOVA has an F statistic. This is called your test statistic. So my test statistic for this one is F, okay? So next class, this is where we'll start. We'll talk about how to find the F test statistic and what it means if you get a large numerator, what it means if you have similar variability, or what it means if you have a small numerator, okay? We'll talk about what each of those implies for our groups, all right? And then we'll actually start running the test, okay? Any questions before you go today? No? All right.